Hello everyone and welcome to Solved, where we help you solve problems. In this video, we will be performing calculations to determine the efficiency of a turbine. Here's the problem statement. A steam turbine operates adiabatically to generate 3,500 kilowatts. Steam enters the turbine at 2,400 kilopascals and 500 degrees Celsius and exits as saturated vapor at 20 kilopascals. Determine the mass flow rate of steam and the turbine efficiency. Let's go ahead and solve this problem. Here is our illustration of the problem. We have a turbine given the inlet's pressure and temperature conditions for steam, and our outlet is saturated vapor at 20 kilopascals. It was stated that the turbine generates 3,500 kilowatts of work. Since it is the one generating, in our energy balance, the work term should appear as a negative value. We are required to solve for the mass flow rate of steam and the efficiency of the turbine. While the type of efficiency to be solved was not specified in the problem, in this case we will solve for the isentropic efficiency of the turbine. Let's begin by determining the mass flow rate of steam. Since this is a steady-state open system, we can begin our solution straight with the first law of thermodynamics analysis. Our energy balance would become the mass flow rate of steam multiplied by the change in enthalpy of steam plus the change in kinetic energy plus the change in potential energy, and that is equal to the rate of heat transfer plus the rate of shaft work. For this problem, we can simply assume that the turbine is adiabatic and kinetic and potential energies are negligibly small. Since we will be dealing with an isentropic efficiency, our base case assumption for the turbine is it is adiabatic and reversible. Our energy balance equation simplifies to the rate of shaft work is equal to mass flow rate times delta H. Delta H in this case is simply H2 minus H1. We can determine the values of H2 and H1 from steam tables. For this problem, I will be using the steam tables from Fundamentals of Thermodynamics by Borgnacke and Sontag. Here is the steam table for saturated steam. Our stream 2 is saturated steam with pressure of 20 kilopascals. So we have a separate table here for the pressure entry. We see that at 20 kilopascals saturated vapor, we then determine our value of H2 to be 2,609.70 kilojoules per kilogram. For stream number 1, our pressure is 2,400 kilopascals. So we can actually see from this saturated steam table if our input is also a saturated steam. For 2,500 kilopascals, our saturation temperature is 223.99 degrees Celsius. Our actual pressure is 2,400 kilopascals, slightly lower than 2,500, but our temperature is 500 degrees Celsius. That means that by approximation, our stream 1 is a superheated steam. If we go to the superheated steam tables, at 500 degrees Celsius, we have to interpolate between 2,000 and 2,500 kilopascals to determine the specific enthalpy of stream 1. So we are interpolating between 3467.55 and 3462.04. Upon interpolating, the value of H1 is equal to 3,461.82. Now that we have the values of H2 and H1, we can go back and solve for the mass flow rate. The mass flow rate is simply equal to the rate of shaft work transfer divided by H2 minus H1. Substituting our given values, our work is negative 3,500 kilowatts divided by our delta H, that is 2609.7 minus 3461.82. Our mass flow rate of steam is equal to 4.11 kilograms per second. For the next part of the problem, we are asked to determine the isentropic efficiency of the turbine. We define the isentropic efficiency of a turbine as the actual work generated over the isentropic work. The actual work was already given, that is 3,500 kilowatts. So all we have to do is to solve for the isentropic work. This can be determined by the mass flow rate multiplied by the enthalpy of stream 2 prime minus the enthalpy of stream 1. The enthalpy of stream 2 prime is the enthalpy of stream 2 if we are carrying out an isentropic operation. That means that we have to determine the entropy of stream 1, apply that entropy to stream 2, and then determine the enthalpy of stream 2 if it has the entropy of stream 1. Okay? Let's first determine the specific entropy of stream 1. Going back to our steam table, at 2,400 kilopascals, 500 degrees Celsius, our system is a superheated steam, and we have to interpolate between two values of specific entropy. We are interpolating in between 7.4316 and 7.3233. Upon interpolation, we have determined that our specific entropy for stream 1 is equal to 7.3450 kilojoules per kilogram per Kelvin. Our determined value of the entropy of the input stream, that is stream number 1, is also equal to the entropy of stream 2, that is under isentropic conditions. So for stream 2, we will no longer be following the given that it is a saturated vapor. We have to rely on the given value of the outlet pressure, that is 20 kilopascals, and the outlet entropy, that is the same as the inlet entropy, to determine the value of H2 prime. Remember that H2 prime is the enthalpy of the outlet stream if we are carrying out an isentropic process. Let's go back to our steam table. Let us take a look at our saturated steam entries, and then we will look for 20 kilopascals of pressure. For a saturation pressure of 20 kilopascals, our specific entropy ranges from 0.8319 from the saturated liquid to 7.9085 for the saturated vapor. Our specific entropy is 7.3450. It is in between, meaning that our stream 2 is now a saturated mixture. It's a mixture between saturated vapor and saturated liquid. For that, we have to identify the quality of the steam before we apply that to the enthalpy. We can solve for the quality of the steam using this equation here, that is our actual entropy minus the entropy of the saturated liquid divided by the difference between the specific entropy of the saturated vapor and the saturated liquid. Substituting, we have 7.3450 minus 0.8319 divided by 7.9085 minus 0.8319. Our steam quality is 92%. We can now use this value of the quality to determine our H2 prime. For that, we have to take a look at the values of the enthalpy of the saturated liquid and saturated vapor at 20 kilopascals. For the saturated liquid, we have 251.38 kilojoules per kilogram. And for the saturated vapor, we have 2,609.70 kilojoules per kilogram. We can now rearrange our formula for the quality to determine the enthalpy of our outlet stream for isentropic conditions. We have H2 prime is equal to the enthalpy of the saturated liquid plus quality times the enthalpy of the saturated vapor minus the enthalpy of the saturated liquid. Substituting our obtained values, I will be starting with the quality. We multiply this with the difference 2609.7 minus 251.38 plus the enthalpy of the saturated liquid, 251.38. The value of our outlet enthalpy for isentropic conditions is 2,421.91 kilojoules per kilogram. Let us now use this value to determine our isentropic efficiency. If you compare the values of our H2 prime with that of our H2, remember that H2 is the actual enthalpy of the outlet stream. You would notice that the enthalpy of the outlet stream at isentropic conditions is lower than that of the actual conditions. That means that for isentropic conditions, we will be able to extract more work out of your steam. Solving for our isentropic work, we have our H2 prime, subtract that to H1, 3461.82, and multiplying this to our mass flow rate, 4.11 kilograms per second, we have our isentropic work, negative 4,274 kilowatts. That is higher than that of our actual work. Remember that the negative sign here implies that the turbine is generating the work. Okay? Now finally, solving for our isentropic efficiency of a turbine, we simply divide our actual work, negative 3,500 kilowatts, with our isentropic work that we have determined earlier. And the efficiency is 0.82. That means that our turbine is 82% efficient. Our interpretation of that is this turbine can extract 82% of the isentropic work. Okay? For these types of problems, whenever efficiency is involved, especially if we are talking about isentropic efficiency, you should expect that the values of entropy of the streams will play a major role in the solution. That's it for this video. Thank you for listening and consider this problem solved.